Dear participants from Shanghai venue, please mute your cell phone and computer. The meeting will start in 2 minutes.
Good afternoon, ladies and gentlemen and colleagues, and good morning for those colleagues online from European countries. On behalf of Chinese Academy of Science, Earth Science Division, and also Division of Earth and Environment from European Academy of Science, and we are very happy to welcome you to join us for this forum meeting. Would you please show the slide, please? Okay. Yeah. We have two conveners. Professor Prof. Tréguer from University Press and myself. This is the third meeting between two academies focused on the ocean science and technology. Now I would like to welcome Dr. Deng Pan to deliver opening speech on behalf of Earth Science Division and Chinese Academy of Science. Deng Pan, please.
Thank you, Dr. Zhang. Dear forum chairs, academicians and experts, good morning to online friends and good afternoon to everyone. It gives me great pleasure to gather with you in Shanghai to participate in the forum on the progress analysis of China-Europe ocean science and technology, sponsored by academic divisions of the Chinese Academy of Sciences, in short form CASAD, and organized by Division of Earth Sciences and Academic Works and Publication Committee of CASAD. On behalf of Bureau of CASAD, I would like to extend warm congratulations on the successful convening of the forum. Sincere thanks to all attending academicians and experts for their support to CASAD. We would like to express our gratitude to East China Normal University and China Science Magazine that co-organized this forum event for their careful preparation and thoughtful service. The Forum on Frontiers of Science and Technology is an important academic activity of CASAD. The purpose of this forum is to promote the exploration of cutting-edge scientific theories and technologies, deepen the research on disciplinary development strategies, promote interdisciplinary integration and international academic exchanges, discover and cultivate outstanding talents, advocate scientific democracy, encourage academic competition, and fully plays a leading role of CASAD in China's scientific and technological frontiers and innovative development in the future. Since its establishment in 2011, it has always attached great importance to leveraging the professional advantages, academic influence, and open connections with scientists across the country. It organizes and gathers high-level scientific and technological talents at home and abroad, conducts in-depth exchanges and discussions in important fields, and plays an important role in academic leadership, talent cultivation, scientific and cultural inheritance. Its academic reputation and influence continue to improve, and it has gained recognition from the scientific and technological community. In the future, we will further leverage the advantage of the open academic exchange platform of CASAD, make the forum play a more active and important role, strengthen the construction of the talent team, and actively create a good academic and cultural ecology. This forum is the 184th academic event since the establishment of the Forum of Frontiers of Science and Technology, focusing on discussion in the field of ocean science and technology, which is of great significance. The 12th Standing Committee meeting of the 17th Division of Earth Sciences decided to organize a forum led by academicians Dr. Zhang Jing and Dr. Tréguer, inviting a group of experts and scholars who have achieved excellent research results in recent years. Through extensive exchanges and in-depth discussions, the forum will systematically summarize and sort out the current development status of relevant fields, analyze cutting-edge trends and directions, discuss future development strategies, and review the internal logical laws of the discipline. At the same time, we hope that the forum can play a demonstrative role in discovering and cultivating talents, and a leading role in promoting academic exchanges. According to the management regulations of forum, the forum adopts a combination of theme reports and free discussions, and participants are particularly encouraged to freely discuss around the theme. We hope that the forum can produce high-level results. We will form a forum overview and share it with everyone according to the procedures and channels. We will also summarize strategic research results to form academicians' suggestions and submit them to policy reports, providing consultation and suggestions for the development of relevant fields in the country. We also encourage everyone to publish research results in the magazine, Science China, and Science Bulletin. Finally, I would like to express my gratitude once again to all the academicians and experts for their active participation and support. I would like to thank the forum convener, and all the staff, and wish this forum a complete success. Thank you all.
Now I have pleasure to invite our convener, Professor Tréguer from European Academy of Science to deliver an opening speech. Paul, please.
Okay, thank you all, and hello everybody. So this is the opening session, of course, and I would like to say first a few words on the European Academy of Science. The president is Professor Rodrigo Martins from Portugal, and the vice president is Professor Alain Tressot from France. We are a very young academy, actually, because we were founded in 2003. A number of fellows is more than 800, with honorary members like Nobel Prizes and field medal. And we have 9 divisions, including the Earth and Environmental Science division, to which I belong, actually. So, but the objective of the Academy is to promote fundamental research and excellence, and to contribute to the development of the European policies in science and technology, and also to identify the most important problem in science and discuss a way for their solution. Regarding the membership, so we Academy award excellence in science and technology by electing fellows and honorary members, and also award Leonardo da Vinci Medal for outstanding lifelong achievements, and Blaise Pascal medals for outstanding personal contribution to science and technology. So, we'd like to remember that the China-Europe Frontier Forums on the Progress in Ocean Science and Technology are organized under the framework of the United Nations Decade. And so the first one actually was organized in 2020. It was held in Shanghai and online, and around 3 themes. First, ocean-based solutions for climate change and mitigation and adaptation. Also, the making of global coastal ocean sustainability, and the digital twin of the ocean initiatives. And these frontier forums highlight the need to develop capacity building to organize two-way exchanges for earlier career scientists. The second one usually was online because of the pandemic, and it was held in September 2022, around 4 themes: ocean-based climate actions, big management data for ocean science and technology, again, digital twin of the ocean, component of the digital Earth system, and also on the global coastal oceans. And the Frontier Forum support the creation of IPOS, International Panel for Ocean Sustainability. So let me give you 2 elements of context for the first Frontier Forum. In 2014, actually, the prediction for CO2 flux was as follows. So if we are able to stop the use of fossil fuels rapidly, so you will follow the green line, okay? If not, let's say the business as usual scenario will follow the red line. Of course, we have a lot of intermediate scenario depending on the economical actions. It's bad to say that the prediction for now is that we are expecting to have an increase in 3.1 degrees Celsius at the end of the century, except if a drastic change in national contribution are managed. Second element of context, of course, is the venue of the United Ocean Conference next year in June, in Nice, actually in France, which will be preceded by the One Ocean Science Congress, to which we encourage you to participate. So the third Frontier Forum actually comprises 4 sessions. The first one deals with artificial intelligence and digital twin of the ocean. And number 2, ocean ecosystems and carbon cycle. And number 3, coastal ocean and sustainability of society. And number 4, ocean technology and observation. This is for the first time discussed in this Frontier Forum. So this is about all, and I'll use the floor to us. Thank you.
Thank you very much for the presentation and speech. Next, we have any notes from the organizing committee, active one, and please.
So as you may know from the booklet, this session, the whole session will be open to the public. And the whole entire session will be recorded and in the meantime, live stream on YouTube and co-share. 所以各位专家如果有什么敏感的或者保密的问题，请大家多加留意。All right. Any other things to add?
According to our schedules, we don't have a fixed coffee tea break. So that's if you want to drink a coffee or tea, please enroll by yourself. Thank you.
Yes, dear participants from Shanghai venue and online. So if you attending from Shanghai venue, please mute your laptop and Zoom audio to avoid echo. If you're attending from online, please keep your Zoom muted when you are not speaking. For the Shanghai venue presenters, please copy your presentation to the control desk at the back of the room. If you prefer to use your own laptop, please inform us in advance. A timekeeper will provide reminders with a ringing 2 minutes before the end of the presentation. And online participants are required to use their real name to join the meeting. Please use the chat box in Zoom or the live stream platform to comment or ask questions. The moderators will read it. So all the sessions will be recorded and shared online after this event. For any technical assistance, please contact the IT support. Thank you.
Thank you. Any information to share before we move to our next section? Is there any information from your side to share?
Not so far.
Okay, thank you.
I
Now
guess the first.
Louis, Professor Louis Zhang have information to share?
No, there is nothing special. I'm just listening. It seems to be going well, and it will be just interesting. How many people are there in the room in Shanghai?
Yeah. We have about 30, roughly 30 around.
Okay, that's good.
Count the numbers of people in the meeting room.
Yes. Just to know, it's interesting, and of course, I would have liked to be in Shanghai. I was in China very recently, but I could not organize to stay over and participate in person in the meeting in Shanghai, which I'm very sad about that.
Yes, too bad indeed, yeah.
I would suggest that we make a group photo.
Yeah.
Yes.
So
then we start to have session 1.
Yeah, for the people in Shanghai, it makes sense, of course, to have a group photo all together. But for the various participants, maybe you can have a photo every time they make a presentation, and then put that all together at the end, because, of course, the presenters, speakers, they are not all here right now, but they will appear during the 2 days. So maybe every time they make a presentation, you take a picture and then you create a mosaic of these pictures later on.
Okay, go do that. Thank you.
Yeah, that's a very good idea.
Participating online. Okay, so we move to make group photo. Okay, please move. We have a group photo over there. So
So there is a group photo.
keep your
So Pierre, everything okay?
Yes, everything is okay. Yeah.
So finally, the presentation is a video presentation.
Right. Yeah.
No problem. Yeah. Okay. Which means Arnaud actually is at the COP 29. That's who?
I guess. Yeah. Yeah.
With Karina. Yeah.
Yes.
Okay. I've seen Sume in the participant. Hello, Sume. Good afternoon. She's mute so far. Yeah.
You are good morning.
Yes, thank you. Good morning for me. Yes. How are you?
Fine, thank you. And how are you?
Oh, well, quite well. Okay. Except for trouble with an eye. Quite well. Yes. Not sure, but I've seen Dongyong is a participant. Dongyong Su.
I think so.
Yes. Okay. Hello, Dongyong.
I will ask him.
Quentin is also online. Hello, Quentin. Okay. Still mute.
Please come back your seat. We do not have break. We will have a first session. Anybody in the room? Okay. The meeting owner told me we have a few minutes to take a break, so we can come back in the 3 after half. Okay, that's for a 5 minutes break. I saw almost everybody in the room already said, and okay. Since everybody in the room,
And we will start the first session. The first session is AI and the Twins Oceans. Will coordinated by me. My name is Yandu, and Professor Pierre Tando. Professor Tando, could you hear me?
Yes, I can hear you. Can you hear me?
Yeah, I can hear you. Yeah. Actually, this session is equal last time in the 2012. At that time, it's a digital trends of the ocean and a combination of the digital Earth initials. That time, the chairman is Martin Richberg and Professor Dr. Chen. And this time, the session is holding including the first session. I'm a photography and I come from South China Sea Institute of Ocean Knowledge, Chinese Academy of Science. My colleague in the France, the Pierre Tando, he come from the RMT Atlantic at Brest, France, I think. His field is mathematics and its application in the geophysics. I will turn to the Pierre. Could you introduce the first speaker and tell the first talk?
Yeah. So first of all, I would like to thank the organizer to organize this very nice meeting. This is very well prepared. I'm very happy to be here. This is my second Frontier meeting. I did a talk last time, and now I'm very happy to be part of this first session about AI and Twin Ocean. I would like to say that I'm teaching applied mathematics for oceanography at IMT Atlantique. It's engineering school in Brest, in France. And I am in charge of a master program. This master program is called Data Science for Oceanography. So this is completely in line with this session. And really, I'm happy to be here and to talk about this. So to introduce the first speaker, Alain Arnaud. Alain Arnaud is part of Mercator Ocean. So Mercator is the major operational oceanography system in France. And Mercator Ocean is also leading what we call the European Copernicus Marine System, which is a huge institution in Europe to get some fundings especially for oceanography. So this is very important for a French and European community. And so Alain Arnaud is not available today because he's part of the COP29 at this moment. So he cannot join, unfortunately, the meeting. And he did his presentation with Carina van Schuckman, who is also part of Mercator Ocean. And unfortunately, Carina is also at this COP29 conference. So they prepared a video for you. I hope this will be clear and then if you have some questions, we can send the question to them, and if they are connected, we can get the answer maybe today. So what I suggest for the next presentation is that we can hear, I think it's 15 minutes presentation. And if you have any question, you can write your question in the chat, and then I can send those questions to the speaker by email. And maybe if we are lucky, they will answer you at the same time. So thank you very much. So Jan, can you run the presentation, or do you want me
Good
to
morning.
run the...
Yeah,
I'm very happy
we can see it. It's very clear. Okay.
to be starting this session. I'm going to present you the advances of the European digital twin of the ocean, and especially how we construct that around the different applications. So my name is Alain Arnaud. I am the head of the Digital Ocean Department at Mercator Ocean International, and I'm in charge of this development for the European Union of this European Digital Twin project. So what is a digital twin? I think digital twin, you know, everyone is talking about that. It's very known at industry level, and normally it's based on that. You have a system with some a real system with some sensor. You take information from those sensors. Possibly from that you derive some information with some models. You derive some prediction on future evolution of your system, and you act on that. Some decisions. So it's quite easy when you're on industrial level. For instance, an engine, you can change the speed of the engine. You can increase, let's say, the cooling when it's overheating. But it's much more complex for a natural system. So when we talk about a natural system, normally we used to make some digital models that are really the best modelization of the system. We create also what can be a digital shadow. This shadow being a system model that is in real time or less, or near real time, integrating some information from the sensors. But what is the really complex part here is this possibility to make this return on, let's say, to act from the digital world in the real ocean. And this is something that is not easy, and it's where our ocean applications stand in here to help to support that. So our approach today at European level is this one. We are creating this nice, let's say, digital model here. So with all the information that come from the real world. And when you are trying to push is to push to have some action taken from this information coming from the digital world, coming from science and knowledge, to be used by the real world, by the citizen, to make an easy access of this information to the citizen, and especially to have the policymakers able to use that in order to have some policy, some decisions that will act again on the real world. And we will see the evolution of that through the digital twin. So it's there that you see that every kind of application, for instance, on the marine protection, and to see the impact of that on let's say the real world, and to monitor that with the digital twin is very important. And also a thing very important here is to have the possibility to test in advance, thanks to digital world representation, some possible policies to see if we expect from them to have some impact in the digital world before applying them in the real world. I love this representation of the ocean because you see that there is one ocean, and to be doing that, you know, just at a very small level in Europe here will be meaningless, because what you see that the impact of your action on the ocean is quite limited here, and we need to have this possibility of collaboration all around the world to make this activity really useful. So what we are doing is that by definition, and this is one of the main advantages of the marine community, because the marine community is from the beginning really very open in sharing the data and the application. So what we want to do here is to use those new improvements from the digital world in order to enhance this sharing of data and this common knowledge of the ocean. And we are creating here this DTO infrastructure in order to have the possibility to gather all the data and to offer the possibility to deploy applications to, let's say, enrich this knowledge and to create this mutual exchange. So you bring information, you gain some information in return from the rest of the world. So is why by definition our DTO offer is open already to this collaboration, And we see 3 levels of activities here. One is really for someone that want to know about the information, let's say the marine information, to have the possibility to explore the digital twin ocean. So there will be let's say a low-level access for people to get this information, but without being an expert in that. You have also for more advanced people the possibility to create on this digital base, taking those information, the possibility to create their own applications. So for instance, they could have an all drift system in order to detect where the pollution is going, so taking some information from that. And once you have developed an application, or once you have, let's say, you've been deploying some marine knowledge system, some sensors and things like that, you can contribute to this DTO by sharing your data with the community. It's where, let's say, the novelty of the DTO stands, because we are really pushing to have on this single platform, that could be also federated with other one, the possibility to contribute and share the data. Okay, what is also to be remarked here is that this collaboration is also internal at the European Commission, and thanks to the mission Restore Our Ocean, we have been able to have the different project and different European DG, digital directorate, being able to collaborate. So here it's nice to see that in this project of the European DTO, we have, let's say, the DG RTD that is in charge of the science or the research, that is collaborating with the DG MAR, that is an important DG for the, let's say, the marine world, having some regulation of fisheries and protection. We have also the DG DEFIS, that is the one in charge of the part of the digital application, but much more oriented towards the satellites application and those applications. For instance, the Copernicus Marine Service is part of them. And we have also the DG Connect that is now pushing for the new digital era with the deployment of artificial intelligence, of new high-power computing system. So we have the chance here to be federating those 4 DGs, inside the mission Starfish, EU mission Restore Our Ocean. That really is a big support for this DTO initiative. I'm going to pass you a small movie until you have this representation of that. So on the right side, you see a representation of what could be, and this is real data. So all those small points here are sensors that are currently made available in the DTO. So we put make that a bit more animated. You have the small square flying around that are the different satellites that give you us information on sea surface temperature, on sea level, on ocean color. So we are mixing all that and making that available on the platform to have the development of applications. So we have seen before some ocean modeling, and here we have an example of what could be a plastic drift model. So for instance, we create here, integrating this application, a source of plastic, and you see where this plastic pollution is going to deploy in a way. We have that in this other representation. You see that the plastic particles are going here around and not staying here at Nice level, but going to the south of Mediterranean Sea. So we are really helping here. This is a very powerful tool for users and for the, let's say, the real world to see, to make this marine information and those marine applications accessible. I come back to the previous one when you see, for instance, this modeling of tides in the Netherlands. So a very high resolution model when you see that the river is going upflow depending on the tides. And you have some things also very interesting in the Mediterranean Sea here when you see the different entry of harbor. So it's very powerful. So I'm going to the next slide. How do we do that? So we are mainly federating and cataloging and making accessible first the data, the marine data. So we are here, data coming from different projects here that are deployed here. So you see, for instance, the Copernicus Marine, the EMONNet, but many other ones here that could be that are federated in our data lake. So with a simplified access to that. And this is open. We can integrate any kind of data on that. Then you have the application part, so based around artificial intelligence, as I said, AI, power computing, but you have different applications coming from different projects here. So we integrate all that and we make that available at different layers in terms of physics, but also biochemistry, marine species ecosystem, and sociology information are also available here. So we put all that in this kind of unified digital platform in order to help the development. To understand let's say the interest of that and the power of it is not just another project. I like to take this example. This is a slide that was presented at the UN Ocean Conference in Barcelona in April. And on the right here, you have the different projects that are funded by the European Commission on marine application, marine science. So we have many projects that are funded here. And those projects normally, they have some limited interaction one with the other. What you try to do here, thanks to this digital platform, is to have them interchanging the information, their application, serving more or less the same applications and community of users, also sharing them. And to understand the power of that, it's interesting to see those numbers here. Those 151 projects here represent something that more than 1 billion of funding. And we can, thanks to this, let's say, very thin digital layer, enable to create this critical mass of information of marine knowledge, of science, of people that could interact in order to increase, really, to make a greater good here from the usual knowledge. So, take an example of that, very simple. If you consider that more or less any project is like that, you know, you have a data acquisition system, you have an application system, and you have a community of users that you are serving. So what we do is that we deploy that in our system. So the data are coming here in the data lake. We have the application that is deployed on the engine, and we have an interface to serve the community. And once you have done that, what is really nice is that this tool that, for instance, you have deployed for marine coastal application or modeling or whatever you're interested in, you can share that with the community, and maybe some other people around the world will be interested in deploying that on their own, let's say, area with some specific data maybe, or just with generic data. Sorry. And to deploy this application. So this is really the power of that. You increase the impact of your research thanks to that. And if it's not limited, of course, to marine coastal applications, could be for, we have many fields of application that are there, from let's say trading, ship routing, glaciology, marine food. We have many of them that are deployable on this digital platform. So to complete on that, as I said from the beginning, with this nice representation of the ocean, of this one ocean, this is also endorsed and deployed around some UN project and activities. So first of all, this is fully integrated in the ocean prediction of the Collaborative Center of the UN Decade. So we have here the possibility to federate around the different systems that are already offering ocean prediction at global level. And you have very specific to the digital twin activity, the UN program called DITO, that is, China has a very active part in that, because currently the chair of DITO is Professor Shea, that is in China, and we had the first, let's say, global meeting here in China last year that was very, very nice. So it's really an important asset, and those two UN projects enable to create collaboration and exchange of information between let's say, not just this European world, but some relevant activities similar to that, so to create the interoperability between the projects. So to conclude, I'll say that we are really pushing to have those co-development process in our EU DTO core. It's really important to push not just for very big project, but also to collaborate in the different applications to foster the regional application. It's increasing really the impact of those applications to the marine communities, and it's really by definition, I would say by construction, interoperable, because it's interoperable at European level, but it will be increased at let's say a global level in order to have a better good for our ocean. Thank you very much.
Here.
Yes. So
do you have a question online? I will also ask.
I don't have questions online. I don't see some questions.
Also, if there's any question in the room, we can pass it to the Professor Alan, and maybe he come back later time. I think it's because professor is not online. So video, maybe we can move to next. Here.
Yes.
Should we move to the next talk?
Yes, we can move to the next part if there is no question.
Yeah, I think maybe we can prepare some question, submit to the online. Maybe we can come back into the discussion part, and we can maybe answer at that time. So we can move to next. The next speaker is Professor Dr. Chen. Professor Dr. Chen is a physical oceanography and academic of the Chinese Academy of Science. Actually, he is the director of the Southern Marine Science and Engineering Guangdong Laboratory at Zhuhai. Professor Chen have a mainly interesting, many aspects, including the tropical ocean atmosphere interaction and the general ocean circulation, and the polar ocean and climate change. Today, his talk will about the developing regional digital twins ocean system. Let's welcome Professor Chen.
Good afternoon, everyone, and good morning to our European colleagues online. I'm Dr. Chen from the Southern Marine Laboratory. This lab is in Zhuhai, which is right in the middle of the Guangdong, Hong Kong, Macau, Great Bay Area. As you can see from the title, what I'm going to talk about today is the development of a regional ecosystem. Thanks to the previous speaker, I don't have to explain what a ditto is, but our strategy is sort of different. We start from small and going global. And Alan just, gave us a global framework, then zoom into coastal regions. But anyhow, I remember that a couple of years ago, this very forum, I gave a talk on a plan of the construction of this data system. So today I'm going to report to you the progress since then. How do I? All right. Okay, let's start with a bit of background. The Great Bay Area, GBA in short, is an economic powerhouse in China, as many of you know. With only 0.6% of the land area and the 5% of population, it contributes to almost 12% of national GDP. And the max cities in GBA, you know, is many of you know Guangzhou, Shenzhen, and Zhuhai is one of them, though it's a bit small. What's the I have to use this to which one? This is this one. But it doesn't go. I try. All right. GBA is also one of the most prosperous Bay Areas in the world. In comparison to other Bay Areas such as San Francisco, New York, and Tokyo, we have the largest population land area in our GBA, and more importantly, the economic growth here is the fastest. Next. Still. No. Oh, okay. There's a delay. And geomorphologically speaking, wow, it goes. Doesn't go back now. I don't know what happened. Next. Oh, it should have. Okay. Geomorphologically speaking, the GBA is also quite unique with complicated interactions among physical, geochemical, and geological processes with very high sedimentation rate and rapidly changing waterways and coastlines. As you know, Pearl River network is over 2,000 kilometers long with 8 outlets into the bay. Next. Okay. Oh, there's a delay here. Well, back one slide. Okay, in terms of marine environment, GBA is also facing serious problems, including water pollution, red tide, bottom hypoxia, and threat to all sorts of marine animals, including our flagship species, the white dolphin. Next. GBA is also vulnerable to various natural disasters as listed here. And typhoon is a big problem there. This area is frequented by typhoon. And many of them can cause damage over $1 billion. Next. Therefore, for disaster prevention, environment protection, and sustainable economic growth of the GBA, it is of great importance to build a digital twin system for marine monitoring, forecasting, and the ecosystem-based management. Next. Wow. It doesn't show. Well, the connection is not that good. Anyhow, as the basis, as the observational basis for this data system, we have, you know, now what happened? We have built a multi-component observing previous one and monitoring system that actually that is one of the main reasons we know next. The last one. No, it's not. Okay, this one. Go too far. Oh, but forget about it. It's probably because of the video inside, so it's they're going very slow. But forget about that. So they go to the next one. Oh, you can see this one. What I was going to show is that we have a relatively dense coverage in this area. From all sorts of Okay. In addition to the observing system, we also have a multi-level nested ocean modeling system. That includes a global Earth system model consisting of all sorts of components, and also a regional model for the South China Sea. Then the really high resolution model for the Bay Area. In that coastal model, the highest horizontal resolution can be as high as 2 meters. Next. And also, we have tools for forecasts and data analysis based on AI technology, including image reconstruction, the storm and wave forecasting, even the answer prediction. Next. Now, in order to construct data for the GBA, we have to complete at least 4 tasks. I'm going to go through this quickly. Next. The first task is a data lake for the full life governance of the relevant data. That includes geographic information framework based on high precision data, a collection of various observational data based on Internet of Things technology. I have to address here that many new technologies, AI technologies, will be used in this system, and also a data sharing platform among partners based on blockchain technology, and the data middle platform that does what it do to work with the data. Next one. The second task is data knowledge coupled marine forecasting techniques. In particular, uses to improve the model resolution and efficiency based on AI, and replace the physical parameters in the model, and also realize massive data simulation. Next. The third task is online computation and the multidimensional visualization. There's a big task here is the rendering. You have to use this to make it really the visualization attractive. A requirement here, of course, is a supercomputer and also a cloud service. Luckily, we have one of the fastest supercomputer on campus at Tréguer. I have to say, first data, anyhow, data, this is about the curve is that now we have but left of and oilers are heating and patient look most of you know they all does SSB application work very important. So you know this is it's and resist next. This is the final from this carbon again this area to the very only is the is uh, using a variety of sources for the most applicable branching. And
in the world, digital twins. need skill. From the
very interesting. Technically,
the largest, you have the most serious challenge about this. This news AI.
So thank you very much. The prediction. How do we?
Well, because a lot and the forecast cannot give you a number. We're doing the
maybe we can the feedback and
Very much for your very nice. Try to forecast and I to use from I do model forecast.
yeah, four components. So, which is either drill and the traditional losses small the Bay Area. So the story of the film shows. Okay. Thank you.
thank you.
Yes. Well, Britain was doing is Ifremer. So Ifremer is located and so basically very high surface ocean, space and time. This work population curve. So thank you, Pierre. For okay, thank you very much. Down there. My with pretty hopeful can have you can imagine take from in the Google to the field at the student at the physical valuable give a chaotic nature and forecast it. Value on observe Prof orbit average but synthesize full ocean context element which deploy the new resources. So observation pattern that exist. So one
which is related in some, so you rate the right, you have a more try to trajectory of the phenomenon says that hundred this kind of method and say well and try to stretch again a neural network is in mode so of its the wanted behavior and that can usually gradient of the value of so in order to work when you use it and this is the optimization local can't find the and on the one new data points that go can use one you can hit so me you right so now detail the choice see that so you so rectal say okay so we just it possible say when it represents and so can that parameter of the method formulation. Listing up for the investor. And we have the blue dots apply. Try to use this as a grade as you can even out of statistics. So you need quantity and then so and prioritization and the domestic or plausible kind of trial. So is mentioned. So for I might want you compared with maybe they state proposed say okay I and the idea in current idea is since for proxy the number of can if you want also and it can learn or invest network one formulation to some deep learning enhanced using the gradient Here we have the time instead of taking one better. You also we will not depend on the what vision and really to improve networks have parameters something there is in order those parameters the target that we want to use in example. Yeah, we have numeric. So on the left train is from the simulation. On this example, and our have the simulation. And then in Shanghai map to so the is a bit more smooth. And if we look at the data assimilation, so we can see a lot of finer structure, but maybe with less consistency, which we can, when compared to independent observation, which we can confirm by looking at the actual metrics. So here we have the RMSE and the lambda X, which is a spectral score to quantify the scales that are effectively results. And what we can see is that the 4D VARNet manages to improve the scale result by up to 30%. And so we see that this 4D VARNet successfully learned generalizable prior and numerical scheme from simulation data. So to conclude, so I presented a case study on altimetry mapping over the Gulf Stream current. So we have a turbulent SSH field and some sparse observation, which we try to map. And there is this challenge to try to reconstruct the finer structure, which are not currently resolved. And the two questions I wanted to highlight was when implementing a deep learning method, like we have a lot of choices to make on what do we want to parameterize as a neural network. And here, it's a place where we can really leverage existing approaches and we can benefit from collaboration between different fields. And also how to constitute the training examples, which is especially, which can be tricky when working on an inversion problem where often the ground truth, what we try to estimate, is not available in the large quantity. And so for the 4D VARNet, so we use two neural networks, one to capture the prior cost, the prior knowledge in the regularization cost, and one in the optimization procedure. And to train those two neural networks, we leverage the fact that we have realistic synthetic data over the ocean. Thank you. That's it for me.
Thank you very much, Quentin. Thank you for your nice talk. And I think it's important to, as you say, to put some details in the machine learning procedure we are using for oceanography and for the interpolation of such satellite data. Unfortunately, I think we are a little bit late. And what I suggest is maybe if some of you have questions, we can ask some questions during the discussion. So the discussion will be at 10:30 in France and 5:30 in China. So I suggest to move to the next speaker now and to have the question at this moment. Are you okay, Quentin?
Yes, of course, no problem.
Okay, thank you very much. So to the next speaker, I will introduce the next speaker because he is also the chairman of this session. So the next speaker is Yan Du. Yan Du is a senior scientist at the South China Sea Institute of Oceanology, also at the Chinese Academy of Science, and is a professor at the University of Chinese Academy of Science. So his scientific interest include multi-scale dynamics of the ocean and climate, and is working on air-sea interaction and ocean circulation, and is looking at the extreme events in the ocean and in the atmosphere. So Yan, I think the floor is yours.
Thank you, Pierre. Yeah, this the title of my talk. I will talk about the AR application in the construction of a multi-scale ocean structure. Actually, I'm a beginner of this AI technology. Only started this work a few years ago. This work is cooperated with my colleague in my institute and Professor Jiang. This is the outline of my talk. We talk three parts of them. First part actually is the introduction, is the meter-scale ocean dynamics and then observations, and then we come to the construction of this theta as a surface, and then is the AI technology. So the first part is it doesn't work. Oh, it works. It's not to handle that way. This is a figure. I think it's everybody knows. This is many people have plot this kind of figure. In the last 3 or 4 decades, we work on this, basically on the right side of this panel is from the large scale, basin scale, to the meso scale. The meso scale actually from the chemistry data set. But now we know still that a lot of the process in the upper ocean, at least about a few hundred meters, that's the 80% of the motion actually contributed by the small scale process. This is covered from the 100 meter to the 10 kilometer, and from the hourly to weekly. This is very, very important for our daily life, actually. But this work is still very hard to observe because we have no kind of this course to work on it. This is kind of the satellite mission. It starts from the JOSAT, actually. Like not the movie, not the work. It's from NASA, but we can see with the launch of the SWAT in the last 2 years ago, the data is available from the end of the last year. You can see this resolution at the surface. We can find it's from a few hundred kilometer to the kilometer scale. So the surface structure is very fine, and a very small process we can identify. It's just talk before it's illustrated. It's very need high technology to observe this process. Just forget it. Let's move to next. This is what I learned from the numerical modeling. It's kind of it's provided by the MIT GSM. It's kind of very high resolution model. It's not a movie. It included the tide. So it's globally it's kilometer resolution. It's 2 kilometer. We can find the very small and mesoscale process. In the snapshot of the each snapshot is globally. It's the ocean is very active dynamically. But this result actually needed to the verification from the observations. You know, even the modeling have advanced in today's cutting edge technology have applied these models, but still needed to verify the bias. And we know from the globally the observations, this kind of the observations from the shaping cruise, from the drifter, from the Argo, all this is global. Is a passive detection. Is uneven and in spatial and time, and very scarce in the near shore. The graded data actually the resolution only about 300 kilometers. It's good for climate research, but it's not good for the application, especially for the everyday when the government and the industry needed to information about this the really ocean. Fortunately, we have a lot of the data from the satellite. In last 20-30 years, this satellite have actually covered from the sea surface high, sea surface temperature, sea surface wind, salinity, sea surface salinity, and some sea surface structure from the SAR and the ocean color data set. And the question, the challenge is this is order of the satellite mostly actually concentrated on the sea surface. And the other issue is we have no direct observation from satellite. This is ocean surface current. So the purpose of our study, we needed to reconstruct this ocean surface current. It's understand the dynamic structures. What we do, this is kind of we know if we want to do subsurface correction, we needed to know the dynamic correlation between the surface and the internal ocean. So this is can be integrated from the first way is theoretically from the dynamic part because the surface and surface connection. The second, we want to use the AI technologies. So the next second part is first the reconstruction of this high resolution data set based on the dynamic method. Yes. For example, why we do this? Almost every oceanography use the OSCAR data set, especially for the study the climate variability. The OSCAR is very good actually in most of the global oceans. The only issue is in the equatorial region, we can calculate the correlation between the between OSCAR and the surface drifter. We can find the correlation is very low. It's 0.2 or 0.3. And that means there's a significant errors in the equatorial regions. So we needed to do this. Why the OSCAR have some bars in this area? Because most of the OSCAR adopted the equation in the middle of that's blue colors. This is only considered the geostrophic balance and the wind forcing. So we end some terms. For example, in the first term is the partial T term and the advection term, and both of terms, these two terms actually is a signature, include signature, reflect the signature of the meso and the small scales, and the geostrophic part and the wind part actually is large and the mesoscale part. So the result is in the end of the figure, we can find this high frequency and the small scale can be observed, can be calculated use this method. And the only limitation is we have to input the satellite data set, for example, SSH. The satellite data available is 25 kilometers. This resolution is still very low. So we wanted to extend to the kilometer resolution. What we should do? This result also have some new findings. For example, we find this in last 33 decades, that's the increase of the tropical instrumental wave is increased about 12 per kilo. It's very, very large actually. And for the higher for a high data reconstruction, we use another equation. This is a mesoscale ST conservation equations. We can use this figure, show this resolution can improve. And this is the first thing we can have increased the spatial resolution. Is you know the ST can be the resolution higher at 1 kilometer, so the resolution is much increased. The second, we can extend this data set to the not from the 1993. It's extended to the early stage of the 1980s. So we can get this surface current information at least in last 4 decades. The other things is we can use data set is we review this kind of the very important phenomena and process actually in the equator. Usually we can, from the traditional satellite observation, only can observe the Rossby wave dynamic, Rossby wave signature. But using this kind of the equation, this solution, we can identify this distinguished Rossby wave and the Yana wave mode of the TRW. And this Yana wave actually is centered in the equator side. And also we need to surface we can use construct this kind of data. We also want to extend this current to the deep ocean. One of the methods we use the Argo data set. One Argo is trajectory. It can reflect the moment. That means the velocity at the 1,000 meter depth. The others we can use the temperature and salinity to get the vertical structure. That's use the geostrophic balance. And use this kind of method, we can find this deep in the ocean. The current structure is the variance actually. That's other part. This also can get the subsurface current structure using this linear geostrophic potential velocity equation. Because of the surface process is decreased along with the depths. So the central the figure shows this surface process and the subsurface is just decay with the depths. Both of the method we can reconstruct the vertical structure. This is the result. From this result, we can compare these two of them. We can find compared to this real current. This is considered the deep ocean process. We can enhance the accuracy of the current below the 500 meters, but that still have a significant errors at the upper layer because of the most of the thermocline moment is not fixed. Use this method. So the perspective of this work, we need to combine this dynamic method and the UR technology to increase our accuracy of the subsurface current. This is what we do for the why we need the AI technology. So far we AI technology we have 4 points to improve this data quality. The first thing we need to do improve the surface information. Surface information, because wind, cloud, and the precipitation, actually sometimes we did not have the ST could not be available in the full area. This is a journal schematic diagram. How we get the ocean internal current. We use the surface satellite. We use the surface satellite, and combine with the analysis and training it, and combine input in the use the UNet model and training the model results, and then include the physical part, especially for the deep ocean, the TS profile in the vertical and the enhanced surface circulations, and then use both of them, then get this ocean internal current. Why we do the surface first? Because that's input data have a lot of problem. One of the example is the regional ST solution and the accuracy is not so high, needed to improve. And the second is subsurface salinity and temperature. Sometimes the very low resolution and very spikes. And the subsurface temperatures observation and also have some misclear or some climate depths. So this is something. This is some result. First, the still is I don't know. It's very slow to work. Need to push this several times. We use a RVDC unit. This is constructing the system of temperatures. This is we can find if we could include more modular in this unit. We can find the result with the increase. That's one that means is the highest quality. This is when we include 3 of part of them, we can improve this very close to the highest quality. And this is right. We select the example in the Sunshine Sea. We can find it. We can originally this set we have missed some data set, but use this system which reconstructing the asset data is very good. Actually, the RMSE is 0.42. Generally, globally, it usually reach to the more than 0.5. The second part is 3D ocean temperature. It's a little bit complicated, but I try to explain. It's very not twice. Go back. Yeah. Actually, this unit based it's called the multi-branch constructions. Is the 3. You have 3 branches. The first branch is based on the surface satellite observation and the TS prime to get the 2D convolution and project into the deep ocean. The second part is to extract the large scale signature, actually based on the 1 degree resolution data set. And the third part is we extract the high frequency signature. It's called the RESEN method. In this method, we combine with UNet tools, and that's get the output of the very high 0.1 degrees is temperature data set at the deep ocean, subsurface ocean. This figure is shown at 200 meters. And then we can find the check the result in the next slide. Yeah, this is the movie. Can in the 200 meter. This temperature is actually is high variation. It's kind of the propagation from the eastward to into part of to the Sunshine Sea, and part is along the follow the crystal, even reach the crystal extension regions. The RMSE we can find compared to the 1 degree model, the error is much reduced. This we can find is at least 30 or 40% of the errors is reduced. And we use different of methods to check the result. It's the blue one, actually the highest we can we can have a much improvement in the thermocline and the deep ocean. But only problem at the surface still a little bit high. But if compared to original, the 1 degree data set is much improved. This is for the salinity. This is for the temperature. And then we check the salinity. Sorry, it is salinity. Salinity, we use other method, it's called FFAN. We actually do not know why it's different from the FFAN and the UNET method, but for the salinity, it's FFAN, this method is much better. This is also result. This salinity at and combined to the, this is the right panel actually we expect the data will finally the current based on the satellite sea surface observations. We in the future, our perspective is this. The part need in
mediation and in this model, mimic gas from biochemistry. So it does present
this is that might be so it's the region use this adaptation on the bottom right, then models both the atmospheric model and your application technology model as the impact feature we define as average is pipeline. And it's years, and y-axis the net primary productions. Each dot corresponds to an annual indicator, and the line corresponds to the 30 years average. And what you can see is that we expect for this indicator, we expect a decrease in the future. This follows. This is in the IPBS report. This is what is the result which is expected. We expect a decrease in the future of this indicator. And this is an example of feature we use. So here I show you the sea surface temperature in July. So each dot is again a climate indicator here, and the line corresponds to the 30 years average. And we can see that we expect an increase of sea surface temperature in this area. And basically, this slide summarizes our approach. So it's in 2 steps. So the first step is training. So we train with the historical period and the scenario RCP 8.5. And we use something called symbolic regression that I'm going to explain you after that. And what it does, this symbolic regression, is that it finds automatically an equations, mapping the features to the target. Then we use this simple equation that we find on the test set, on the test scenario. So the test scenario here is RCP 4.5. So we have access to the data for this scenario so that we can check if our equation work well on this scenario. So here I show you how does it work, symbolic regression. So in my case, I use a Python library called Pyser. So this library works using genetic algorithm. And usually, most library for symbolic regression works like that. So the objective of symbolic regressions is to search through the space of functions to find the optimal functions that match your data. So here, for instance, so how does it work? It represents any function as a tree. So for instance, here there is the equation x times x minus y. So we can represent it as this tree, and then it learns the coefficient, but it also learns automatically the structure of your equation. The only thing you have to give are the operations it will use in the equations. So in my case, I give some simple operations, so the plus, minus, multiply, and divide sign, but you can add many other operations. And that's the only thing you have to give, and then it will learn automatically an equation. So we apply this for training. So basically, this kind of algorithm, there is one limit that it cannot take many features. So 300 features is too much. So we first select 5 features. We're using some feature selection methods. Basically, we try 4 of them, 4 different methods, and we apply that to the training set. Then we do some cross-validation on some validation sets, because this method has many hyperparameters, just like deep learning models. And finally, we select the discovered equations that minimize the prediction error on the validation set. So this is, as Pierre told you, some preliminary results. So first, what we do is to compare Pyser with other models. So we compare the results, the prediction with our equations to other machine learning models. So on this graph here, on the x-axis, you have the different models. On the y-axis, you have the root mean square error, and the bar corresponds to the prediction error on the test set, and the cross corresponds to the prediction error on the validation set, and basically, and the colors to the different feature selection method. And what you can see is that on the test set, the top 3 ranking are reached by Tréguer, so the algorithm finding automatically equations for the two best. It ranks the 2 best scores, and then it's linear regression. But we are kind of surprised by these results because we would expect that more powerful algorithm, but just like random forest and gradient boosting, should perform best as this method. These methods are like random forest are really not interpretable, but it should works better. So it's kind of surprising results. The second surprise is that in our results, the main variability seems related to the choice of feature selection method. And so it's kind of weird. And so the next step for us would be to improve the feature selection. So what here is just, so here we look at the best results. The best result was the equation with the blue feature selection method. So here I give you some details on our results. So what the algorithm does, the algorithm that finds automatically the equations, I kind of lied to you. It doesn't find one single equations, but what it finds is something called the Pareto optimal set of equation. So on the x-axis here, you have the complexity, and on the y-axis, the root mean square error. So the complexity, it corresponds to the complexity of the equation. And basically, how do you compute it? You just compute the number of terms of any equations. So for example, for the complexity 3, here we have a variable, the minus sign, and a constant. So it makes a complexity of 3. And what the algorithm Tréguer does is that for any complexity, it's capable of finding the best equation for this given complexity. So it's kind of cool because in the end, you can really just analyze this graph, so this Pareto optimal set of equations, and you can see it's kind of a Taylor expansion, but for equations. So it's kind of nice because you can really interpret and find yourself maybe another equation that is simpler than what is the optimal equations. So this is what we find in our case. So in our case, if we look at this graph, we observe that for the test error, so the blue square, that for the complexity 11, there is a simpler equations that has better score than the equation that was selected by the algorithm. So next step for us would be to improve the selection of the equations with a better trade-off. So to conclude, so what we propose is some methodology, a general methodology for any climate application. So the goal is first to discover using symbolic regression an equation with the historical period and the scenario RCP 8.5, and then use this equation to predict impact indicators for the other scenario, such as scenario RCP 4.5. And we apply, in our case, this methodology to the net primary production of phytoplankton in the Gulf of Lion. And next step would be to improve feature selection by mixing interdisciplinary expertise and automatic machine learning. Thank you for your attention.
Thank you, Erwan. Thank you very much. Maybe Jan, do you have any?
Is that we're really just trying to emulate the models. So if the physical models we're using is wrong, basically our equation will be wrong. But if the model is quite good, and the question, if I understand well, is how to check that this equation we find is good enough. So one way to do it is what we did is that to check on the other scenario if we still find the same equation. And another way to do that, to answer your question, is to use observations. Can we learn with these climates? So the model was used with climate scenarios, so we can learn the equation from that. And then can we use observations to check So if we have access to observations for the variables of interest, for example, sea surface temperature and this kind of thing, can we check that with empirically the equation that we find also holds? Or we can do this the other way around. We can learn the equations and observations and then use the equations for our application. So this could be an idea of application.
Okay, thank you. Thank you, Evan.
You're welcome. You're welcome.
Jan, I think there is a question from Paul, right?
Yes, it will be a very quick question. Not sure what was the answer actually. When I have a look to your slides.
Paul?
Hello? Do you hear me?
Paul, do you have questions?
Sorry. So my question is, when you have a look on your slide showing the prediction regarding the variation of the primary production, the net primary production versus time, okay? This prediction might be very different if you consider phytoplankton, large and small phytoplankton. This is a way we have to discuss. We need time to discuss that later. Okay, thank you.
With pleasure. Thank you.
Thank you. I think it's time to go from the next speaker, right? Yes, I cannot hear you very well. Sorry.
Okay. You can show us that the voice is it's too much noise. Can you fix the problem? So here you can turn the right, but there's the noise.
Sorry, I'm not sure to understand what you say.
Pierre, what about?
So, Yan, can you introduce the last speaker, Shangming Dung?
You can hear me, right? Could you hear me now?
Yes, now I can hear you perfectly. Yes.
That's great. Yeah, that's some problem in last 2 minutes. Some connection, I think.
Okay.
Let us move to the next speakers. Actually, this is the last speaker, but not the least. This Professor Changming Dong. Changming Dong is physical oceanography. Actually, he's dean from the Nanjing University of the Information Science and Technology. He also a chairman of the first AI Oceanography Association in China. Actually, the talk today is the AI application in the oceanography. Let's welcome Professor Dong.
Okay. Thanks, Professor Jing Zhang, the chair of the forum, for the invitation. Give me opportunity to share some idea about the AI application in oceanography. I'm from the Nanjing University of Information Science and Technology. Okay, so I'm following the AI application in oceanography for more than 5 years, and then in 2018, I supported by the company which is called Universe. This is the company to working with me to set up all the AI oceanography, the academy, in 2018. Then since then, I started working on the AI oceanography. And then 2 years ago, I published a textbook on AI oceanography fundamentals and applications. This textbook has been used many the university in China, which is in the Chinese version. And today I'm going talking about the three parts and most focus on application in oceanography in four perspectives. Okay, so it's AI and the big data. It's the two very popular concepts recent years. What's the relationship between the AI and big data? The big data is like a mine. You have a gold mine, then you need good tools to dig out that, to make use of this mine. So look at this. The ocean data is have the numbers or the volumes and numbers. It increases dramatically you can predict in future with the more satellite data and more observation in the ocean. So it's more and more data is including like different data like a digital elevation model, like what the sea, the depths, the water depths, and in situ observation data, remote sensing data, numerical model data. So all these data to combine all the it's to make the oceanic data become bigger and bigger, and then generate the big data. The big data and then the data is a different concept. So the big data, which carries of the five-way the characteristic like a volume, velocity, and a variety, and a veracity, and the values. If the data is a false data, you cannot be considered the part of the big data. So if the data is doesn't change with time, and then data is not can be considered the velocity means the data keep updated. So if the data can be considered as a big data, that means which carry five-way characteristics. So besides the data, also the derived data, for example, our global oceanic mass eddy data set, which carries atmospheric and oceanic biological the variables, which is also part of the oceanic big data, which is derived data, is not original observed obtained data. Okay, so for example, this published EOS 2018, that's two scientists, they mentioned now the oceanic or even the earth science, the development in two directions. One is use more and more data driven, the method and the direction. Another one is the physics or chemical and biological based the developed directions. So these two directions, which the key point of how to make use of the big data, get more the more understanding of the real world. So how to make use the big data more efficiently? Now recently it's like AI we are using more and more now. So that's the fundamental method is just that you label the real data and your focus data, which generates which is called cost function. Then you minimize the cost function. Just feel the talking about how to minimize the cost function. That's all the call error function. That's actually you find a very efficient way to downscaling or efficient way to minimize the error. Then this method is a machine learning method provides the efficient way to do that. For this is basically like the mathematical equations to just calculate the gradients. And there's many now. It's many the different methods in the machine learning. For example, convolution method, which is focused on the specific the essential features in the data. That's convolution which is used. So then you, for example, you have many features. Many. For example, that's the Yandu, the Professor Yandu just mentioned that the multi scales. Which if we will focus on the small scale, the essential features, then using convolution, then take out the essential part and ignore others informations. Then so that make the efficiency. So these are many. I just give you an example about this AI method. Okay, the application. So due to the time limit, so I just talking about this four part. And there's more and more papers published in journals about the AI application in oceanography. I summarize them and put them into four categories. The first one is the AI-based oceanic feature detections. It's like detect eddies, front, and algaes and different edges, and also they're using the AI to forecast out the oceanic variables for temperature and wave and ENSO and storm surge, and also we're using the AI to parameterization of the turbulence mixing coefficient, and that's a turbulence model. And also you can use AI to solving the governing equations. So if we look up all the papers which will be the paper related to the AI and oceanography applications, you can put in one of the categories. I give you the few very brief examples to share with you guys and different applications. And finally, I will talk about the digital twin. Actually, Professor Dr. Chen has mentioned that already. Okay, so the first one is AI oceanic features. It's many different features like oil spilling, internal wave, sea ice, and maritime vessels detection. And today I only talk about the eddy detection using AI method. And in 2019, and this is 2019, we published the first paper using AI detect oceanic eddies. And actually, we last decades, our group developed a series, the eddy detection, based on dynamics, the features of the eddies. And the top one is we call vector geometry-based eddy detection schemes. And the bottom one, we're using the parameter scene passing network. So we are not going into detail how to be using this method to detect eddy. Actually, that's going back slides. We using this is the tool to label the data, and then using this data to calculate this error between them and minimize the error, and finally to get this method to smart enough to then let you detect the eddies. And you can see some results, and you see that it's the red is the vector geometry based the traditional eddy detection scheme, and PSPNet is a neural network. It's AI based. You can see the correlation is similar. It's over 90%. But you're going to find out that you find out the AI based method find more eddies than the traditional method. And then we could look at in detail actually the small eddy, the AI can smart enough to find the more small eddies. And this is the first paper our group published on using the AI method to detect eddies. And then we applied the more AI based the method to detection eddies. The 2021, and it's others the figures, the comparison. And recently we published another papers to detect the AI-based called 3D. We combine a different method together. We call 3D UNet, resonant network to detect 3D eddies. So this paper published on the oceanic models. That's the same author, my PhD students. Now it's a graduate already. Okay, so another one is AI-based forecast oceanic variables. Then the first example is ENSO predictions. And this is a paper published on Science by Ham and my co-author by my colleagues, Professor Jing is on the Science in 2019. The paper is the first paper using AI method called CNN to forecast the ENSOs in the internet, in the community. So that's immediately caused a lot of people's attention to see AI can using AI to forecast the ENSO and actually do better job than the traditional approaches. And recently, you can see more and more papers published using AI to forecast the ENSOs now. Another one. We're using the AI to forecast the 2D wave. And the last one is just the index, the ENSO index. This is forecast the waves in the coast, the China marginal sea, in the East China Sea all the way to South China Sea. And you can see that this is comparison, the forecast true and error. And you see the AI forecast can reproduce the true values pretty well, even in the typhoon conditions. This paper published in 2021. This is the comparison and using the with time increase, that's correlation decrease and error increase, but still in the acceptable range. And this is using different the methods, using all the data to the typhoon conditions, the waves, and also you just using the typhoon induced wave for the training. That's results are slightly different. And also improve this wave, the forecast using AI, and put a different method like a convolution method, bias, STM, and also put attention and dance, and using the combination of different methods together, and can see that significant improve this error, and it's a significant improve the forecast the accuracy and decrease the errors. Okay, and the third one is AI-based oceanic turbulence mixings. You know, if you are physical oceanography, you look at the equations, the governing equations, and you can see all the equations is almost accuracy except the turbulence mixing coefficient. And so this turbulence, it's a lot of famous scientists that developed turbulence models, including Professor Chen. He published that's the turbulence models. Integrates different methods together, and that can be used in the Australian and the national climate models. And still, this key point for the use the better forecast, do the forecasting in numerical models. And here it's I think it's almost the first papers using this machine learning method to do the estimate oceanic vertical mixing coefficient. This is published by I think it's published 2022, and one co-author is my colleague Ronghua Zhang, and they are using the observation, the mixing, the turbulence coefficient, turbulence that's observations, and then using the KPP to observe it's a traditional method, the KPP and neural network, and do that comparison. You can see that's comparison that's an increase. I just briefed to show that, okay? And also our group in using the KPP method to compare with using the neural network called backward propagation neural network to compare that. You can see this, this is the prediction, and that's the KPP. You can see we have did the very good the job in using AI method. And the last one is application is solving governing equations. This is pretty much the frontier of the application in AI application in oceanography. Okay, so usually it's this is here I just there's a different method to use to solve the equations with this here I just introduced the called physical informed neural network, and this part I don't think this works. Okay, if without the equation part, just the first part, and you input the location, the time in the neural network, and you estimate the velocity, and you can get this velocity, and you minimize the error and come back to do many steps, and you can get the training the systems. And but this is only the data driven. If you put if you estimate the velocity, the results, and put in the equation, you get another error, and then another error, and put them together to generate the combination, the error cost function, the cost error function or cost functions, and then you put back in the system. So this part, then this system including the mathematical equations. There's nervous equations there. And the first application is which is done by the Racing from the Brown University in 2019. They doing the Island Week, and then can well produced using this method. And also you can do very simple to time variance the approaches. For example, you do exercises using the diffusion equations. You randomly put some number there and put the equation. You can move. It can almost generate the whole areas the values. And more complex is nonlinear the equation. This one is linear equations. If you're doing the nonlinear equations, that's KdV equations, you can also reproduce that using when you put this equation inside. And this is a recent in 2020. He published another paper to solve the 4 equations for the concentration equations and velocity and 3-dimensional velocity. Put 4 equations in the systems, and that's that generates the combination of the error functions. And then he applied to the blood blood motion in the heart. So because the heart, the shape is not fixed. The heart, the human being's heart, the shape is. So when you do this numerical simulation, it's very difficult to generate the grid. But this method, you don't need to fix the grid because the shape can change. So you don't need to fix the grid. You get the result, just plug in these differential equations. You generate error and just send back to the neural network. You can keep moving. This paper is published on Nature 2020. It's then his method. He given another method, the name called hidden fluid mechanisms. Actually, it's just a PRNN. Okay, that's a different name. So this paper published the Science Nature, and immediately caught a lot of attention about his method. So that's he claimed that look, we can put the equations in a system to do the training. Okay, so this I just briefly to give some few examples to talk about the application to oceanography and the digital twin. We have 2 talks talking about that. And for example, UN and Europe have the detailed programs in for the UN Ocean Decade programs. And in China, we have the field programs running now. For example, the Professor the Dr. Chen mentioned the Greater Bay of the GBA and the digital twin the system, and also in Ocean University of China, they have the digital twin of the cold water mass, and our group also working on this. Okay, it's time limit. Thumbs up. Okay, I just 1 minute. I give do an advertisement, and our group, our university is building the largest rotating tank in the world, and this is related to the digital twin of the rotating tank. I mentioned this one. So we are built the digital twin of the rotating tank, so related to the top talk. And we almost finished. Okay, we are this rotating tank when built up, it's will become the largest rotating tank in the world, and the diameter is 14 diameter in inner circles. Inner diameters is 14 meters. And starting in 2017, now it's almost 7 years. It's almost finished. And that's it. This is the 2 buildings. The round shape of the building is the host of the rotating tank. And this system, this is the pictures of the recent pictures. That's the tank, and this is that's the rotating platform. This is a tank, and I welcome everybody. It's a oceanographer from all over the world, every corner of the world to if you have the program or project to using the rotating tank, you are welcome to use it. Thank you so much.
Thank you, Professor. Very, very exciting talk, and especially for the last routine tanks and combined with the AI technology. Any question from the audience, online or in the room?
Sorry, maybe I have one question.
Okay.
Yeah. Thank you very much for your very nice presentation. It was very instructive for me. You were talking about forecast using AI, and I was wondering if you estimate, I think it was on the ENSO index, And I was wondering if you try to predict only the mean forecast, or are you also trying to predict a kind of uncertainty around your forecast?
Yes, thank you for the questions. So the forecast which it can be using the AI to actually do the same job as the traditional numerical model method. So actually including what you mentioned, the uncertainty, because the prediction, for example, temperature and wind and so all this is all the variables to be forecast. Yes. And for example, so published in 2019, the paper also that's forecast the index, the Nino 3.4 index. And now there's last few years, you see more papers published about the forecast the two-dimensional the pattern of the SIT in the tropical areas. And also for us, we also focus the wave, the variables, the wave, the significant wave height, and including the mean, also the uncertainty. Yes.
Okay, thank you very much.
Okay, thank you, Professor Dong. Let's thank the sixth speaker at this morning afternoon session, and maybe we move to the discussion part. Let's thank you first. And because of the first talk, we have some technical problems. The movie could not play. Could you please to try to again? Because I think that's a very excellent movie. Yeah, just some movie. Also, I repeated some questions for the Professor Chen. Can you just one or two movie? At the same time, the Professor Chen can answer the questions. Yeah, this one I think very important because it's a monitor network. Cost a lot of the funding and the main power. Actually, it's yeah. Just two questions to Professor Chen, and maybe can answer them. Let me check the one of them. The first from the audience in the online, the first question: would you please let us know more parameter in the digital D21 to adapt the forecast of the flood disaster predictions? And also, that's two questions. I see it together. The second question: how to have a more efficient prediction? Yep.
All right. The first question is about flooding forecast. The most important parameter, of course, here is the inundation. So for that, you need a grid system that you need to have wet and dry grids to do that, and for to do a very accurate forecast. I found that the what's really important is the topography, near shore topography, in water depths less than 5 meters. If you don't have that kind of data, you're not going to get very accurate the forecast. So to do that, we have some observational programs for just for the seafloor mapping. Now we're doing that along the whole coast of Guangdong province. Okay, that's for the first question. The other question is about the efficiency, how to make the forecast more efficient. Well, that's the reason we're doing this AI, the modeling, AI forecasting, because traditional numerical models, as I said, is getting into a bottleneck because the computational burden is now so heavy. You cannot use them for really high resolution real-time forecast now. So you have to use data-driven models combined with physical models. So that's one of the advantages, of course, of the AI models. The other advantage, actually, there is that question to Professor Tong, is about uncertainty, because with the AI models, we can, do a very large ensemble. So from that, you can get a more reliable estimate of uncertainties. Okay, that's it.
Okay, thank you, Professor Chen. It's always show some very exciting result and many effort from the Professor Chen's leading the group in this laboratory in the Guangdong. And is there any more talks? This question from the Professor Dong.
For the parting, for the third speaker, is still there?
Yes, Quentin is.
Yeah, Quentin. Okay, thank you. And your talk is very interesting. Due to the time limit, I have no time to ask a question. And so you are the most of it's like you are doing the downscaling, right? So from the coarse resolution to downscaling, get a high resolution. You're remapping the surface height. And you also compare with different method, and your name it's a 4D net method. I record that, right? 4D net method. So what's the you can summarize what's the advantage your method compare with the data simulation. I see you give some the summary. You can give more information about that. I think it's a very interesting, very useful the method you proposed. Okay.
Quentin, we cannot hear you. Sorry.
Can you hear me now?
Yeah, thank you.
Yeah, okay, sorry about that. Yeah, so thank you very much for the question. Maybe a small clarification first. So the problems I try to address is not directly downscaling, but more spatial and temporal interpolation of the satellite data, which has missing values, which has a lot of gaps. But there is this indeed this challenge to have finer scale reconstructed than existing methods. So this is where it can be akin to some downscaling of existing method, but I start from the satellite observation and no, not from a low resolution field. And so for you, the second part, how does it compare to data assimilation method? So the problem statement can really be is really similar to some variational data assimilation problem statements, such as the 4D var, except so in this variational formulation, you will minimize a cost composed of two terms, so an optional observation cost and a regularization cost. And the second cost in the data assimilation formulation is computed using a numerical model, so the physical equation of the ocean, whereas in the 4D VarNet, we will try to learn this prior from numerical simulations. So the same physical equation will be used to generate high resolution realistic fields, and we will capture the prior knowledge from those simulated data after to do the same inversion as in the 4D var problem formulation. So it's really the same framework, except one brick in the variational cost, which is traditionally stated as the integration of a numerical model, is now stated as a neural network. I don't know if this answers the question.
Okay, thank you. Thank you, Courtney. I saw that Paul have a question.
Yes,
Paul?
Also for Quentin, actually. So you rapidly mentioned that you will soon use a SWOT mission. Could you explain what you are expecting from the SWOT data?
So I think there is a multiple way we can leverage the SWOT data. The first one is it's the first time we will have this high resolution data of the sea surface height. So it can first be really useful to evaluate existing method and how the smaller scale are reconstructed or not. So we have these 2D fields. So to compare what we reconstruct from the interpolation with some now actual measurements at high resolution will be really useful. And after, there is this challenge of using this as training data to be able to learn some finer structure. So compared to other satellite altimetry, we have less historical data since the mission is been there for 1 year. So there is, I think it's still an open question all the way we can benefit from this mission, but it will definitely, there is definitely a lot of opportunities. Yeah.
Thank you.
Thank you. Any questions? More questions from the in the room? Actually, I still have a question for the content. Content here. You show the result in the page. You compare the MSE in you compare the DUA ACS and OI technology and Glorious 12, I think, and the 41 net. I don't know if the Glorious simulation, did you also include the SWOT dataset or not?
So is the question if there's a SWOT dataset in the Glorious 12 simulation?
I mean, in the Glorious 12, do you already include the SWOT, simulated SWOT data in this model or not?
So so today I don't know, but at the time of my PhD thesis, I'm sure that it didn't because the SWOT data wasn't yet readily available.
Okay, thank you.
You're welcome.
Just a question from Professor Zhang. Let's just a minute.
Thank you. I have a question to all speakers of this afternoon. With AI technology and machine learning, how successful are you if you are required to make a prediction of biological blooms, like seasonality of phytoplankton blooms in the mid-latitude region?
Okay. Any speaker answer this question? Professor Dong, could you answer this question because you are almost use technology to in most of analysis of those?
I don't pay too much attention to the bloom, but I believe that's based on the data, doing the forecast, using AI mostly it's based on the observation data, the label. Okay, if you have a numerical model, you can do the forecast, numerical model do the bloom forecast. Then you using the forecast results, the label the data, and then you using the many different ways the AI based the scheme to as also you can quickly to get this forecast become available. And of course when you input the there are two approaches to do the forecast. One is just time regression, and then you don't need an external force. Okay, if we're using external force, we're using the mechanisms to the inform, then then the system become different. That's the forced system. So for example, we're doing the wave forecast. We can using just the wave itself to 24 hours. But if you're doing the long-term forecast, for 3 days, you need the external force like the wind. But I'm not expert in the bloom, so I cannot talk too much about that.
Maybe Professor Chen can answer the question.
Well, the short answer is we're not successful so far, but the AI has the potential to do better than traditional models because the traditional ecosystem models are not doing very well simulating the whole process. Well, we bloom, the seasonal cycle of bloom is there. I mean, The hard part is the exact dates. That's hard to predict. But I think AI has potential. That being said, I want to say a few words about the about AI. As we know, the AI is developing at an imaginable rate now. So we don't know. Probably AI itself will provide some answers to our question in the future. But as I see it, as far as oceanography is concerned, we are not really in a big data era yet. The big data we have now, there are only two kinds. One is satellite remote sensing. Well, you can include the radar remote sensing. The other is numerical models. But for satellites, the data is only at the surface. Well, develop some method to extend that downward, but there's a lot of uncertainty there. The numerical models are not that reliable yet now. So for the underwater subsurface, we just don't have enough data, and that's not going to change in the near future. So how to deal with this problem? Well, one way is to invest more in the in situ observations, but that's a slow process. The other way, as I say, is to develop a better algorithms, AI algorithms. Well, the traditional algorithms is based on big data. The assumption there is you have unlimited sort of a data set for model training. But that's not the case for oceanography. So what we're thinking now is to develop algorithms that's better suited for small samples, so-called small data AI, and we need that for our field. So that's what I think.
Okay, thank you, Professor Chen. There's a lot of thought on it. It's remote sensing and numerical modeling. Both of them very important, and but both of them we need some advance in the technology because we still leak some of the observation from the satellite, some parameter. And for the numerical modeling, we still have some parameterization is not work well. For example, for the mixing. Any response from the online speakers? I know did everyone have a response because the geostrophic cycle is very important for this trophy blooming, and particularly its timing window is prediction timing window is important. Any response from speakers on the front side? Okay.
I don't think that. I have maybe one comment related to the last comment, which was very interesting. I think last month I was in a symposium in data simulation for numerical weather prediction, and maybe we have to in oceanography, maybe we have to think about what people are doing in other community which are very close to oceanography, and meteorology is a nice example where they try to develop AI methods. So basically, this is machine learning methods that are combined with data assimilation and uncertainty quantification. So this is, for me, this is a key point for the future of AI in the oceanographic community. So as it has been said previously, there is a lack of observation in the ocean, and a way to extrapolate those data is to use data assimilation using a model to extrapolate the data we have. And there is a nice way of, and people are working a lot in meteorology, trying to use at the same time machine learning and data assimilation, and to use that recursively to increase the number of observations. So this is a this is not real observation, but this is a kind of pseudo observation generated by AI. And also it can be useful for these data assimilation techniques are useful to really take into account the bad sampling of or the errors in the observation and also in the model. So, and this is why also I ask some question about the uncertainty quantification, because I really think that if we want to make a good digital twin, we need to have an estimation of the uncertainty, because I think they
c'est physical, especially past we especially can have security. Quite of a process. Just
and close afternoon and morning, and the digital global and then the contemporary is on the actually routine coverage is very most we use SWOT. Recovery is a study type. Is a that's a productive. To them using the surface information were actually compact. All the speaker.
Thank you very much.
晚饭 as the
One. Can you hear? Okay, welcome back.
This is the second special issue on the carbon sink fisheries. It's about 17 papers. If you're interested, you can check. Anyway, we have the English abstract. If you Chinese very well, not easy to read. My presentation will part 3 parts. One is discover the carbon sink function in fisheries. 2, new achievements. 3, future studies. In 2004, it was found the shellfish and urgent farming has a significant carbon sink function. This brainstorm comes from 2 things. One is inspired by ocean air qualitization experiment in 1995. IGBP annual meeting held in Beijing. I attended that, so I know that. And at the same time, the ocean action of the sand spot. Because during that time, Beijing have a very serious sand spot. The second is filter feeding affection study on the various marine bivalve showed that a large amount of phytoplankton were used during the shellfish groups. This is a carbon budget of the other fisheries activities. The key process of fisheries carbon sink. No matter in which way, the initial process of the fisheries carbon sink function is mainly computed by the photosynthesis. The weighted average of each component of the stock carbon budget is as the estimates needed. There is usage carbon or total carbon require removable carbon, storageable carbon, release carbon. This model is applicable for most of the fisheries, except the feeding fisheries. This is a new term for the fishery carbon. The first time we use carbon, total carbon sink, net carbon sink. The stock carbon budget table 1 for the total carbon sink require the removable carbon account for 21.5%. Storageable carbon account for 41.8%, and release carbon grows to 37%. The net carbon sink require usage carbon minus release carbon is about 63.3%. This is table 1. I think this table the data shows the data so a very good quality. I mean, they have very good working high quality. You see the respiratory state of the various species is completely consistent with the ecological habitat. For example, mussel. The respiration is very low, only 6%. because he liked the very clear water in the open part. And you look the Roger Cram, 46.6 of the dispersion because he's a benthic species, the underground. And the second, you see the 5 species is account for near 90% of farming, 90% of the total production of the farming shellfish. So I think this table have a very good working quality and also have a very good representativity. Is shellfish farming is a carbon sink or a carbon source? Over the past decade, we have read this in the newspaper, but we have not seen any scientific article. With the establishment of the new model of stock carbon budget, the answer is to this question is simple and clear. For example, to go back to think about the table 1. So we say shellfish farming is definitely a carbon sink. The new management method. At present, carbon content method is mainly used. For example, the origin. Net carbon sink is characterized by characteristic, and then the total carbon sink is characterized according to the proportion of this territory carbon release. I should mention that maybe most of us forgot the plant release the carbon. For example, like here, this mean species, a farming species in China is 25%. You go back think about the shellfish, only 90%. 90%. That's 25%. But we shellfish have another release carbon. Oh, the filter feeding shellfish and the fish, I don't see again. You think about the table 1. Capture stock. Due to the multi-trophic level structure of the capture stock, the food web mechanism should be considered. There's a little complex. So you see the formula. So if you're interested, and check the paper. I don't want to. Anyway, it's difficult to do. Okay. The question. Not all the parameters are correct at the present due to the lack of the special experiment research, especially for captures. Now the management method is very simple. The fact that we only one method to think about the forest and others will have many methods to do that. But right now only one method. Okay. New assessment of 2.3 new assessment. Annual variation in carbon sink by fisheries in China coastal ecosystem during the 1979 to 2010. We look after 2000, is a carbon sink increase because the fisheries, boats, agriculture, and pepper fisheries is developed. Oh, okay, I give you some detailed information. It's about 2018 to 20. Macroalgae and shellfish farming. Average total carbon sink is 6.48 millimeter ton, equivalent to 0.87 million quarter of the. I think this is the last word very important. Compressor a ferry station per year. The net carbon sink is 4.0 for 65% of the total carbon sink. Temperature swap is the total carbon sink is very large, but when this account of only 35%. Third dimension, urgent and shellfish farming is 65. So this means marine culture in China have a higher carbon sink efficiency. The reason is very simple. It's because it's more than 80% production from non-feeding species. Carry out special research on the amplification of the carbon sinking in the fisheries, not only applicative research, but also the basic research needs to be trained. Establish various forms of demonstration areas for carbon sink fisheries, including farming disco fisheries, capital. Fishery and
talk with your viewers. Hello.
what do you call? Area. MP.
Due to the discussion part, next will the dance. Or your power. But we
The all know and the year wave is the main goal of the in the atmosphere. It was agreed global warming should not exceed
brain kind of the
very me. I see the
okay, fine.
very and left. Effect. And made the most short of this too very so I really identified this industrial policy efforts that are emissions, the emissions that are difficult or costly. Can be the negative ones. So it's be sequestration. And the carbon emissions. Also, in one with the global, you will be decreased. Well, these are to 20 to that is requires continue of other including emissions and after more which is our blend and in the ocean sensation roof storage with obtained by which in the ocean that which is a storage of the ocean iron fertility involved by dissolved into some will come back after the lens and ocean to enhance the phototopic pressure must which also CO2 sinks natural and will one will come so lower at sinks to into carbon. So this negative wall of sphere and in results the effect of land-based dioxide, the effects figures based carbon coefficient. And the figure shows the reservoir to release you. Deployment of land-based CDR, the net removal of atmospheric CO2 by land-based CDR will be smaller than its gross removal. The difference between gross and net removal of atmospheric CO2 by CDR is called CDR tax. So now we look at the case of ocean-based CDR. And the figure shows that when there is significant removal of CO2 by ocean-based CDR, this causes the land reservoir to release CO2 to the atmosphere. So how to explain this? Well, the flux of CO2 from the atmosphere into the land is determined by the uptake of CO2 by plant photosynthesis, which depends on the concentration of atmospheric CO2, minus, of course, the carbon losses by respiration and forest fires. So the implementation of ocean-based CDR will cause the removal of atmospheric CO2, which will result in a decrease in the concentration of CO2 in the atmosphere. So on land, the decrease in plant photosynthesis, while respiratory carbon cycle feedback to the deployment of ocean-based CDR, the net removal of atmospheric CO2 by ocean-based CDR will be smaller than its gross removal. And again, the difference between the two is called the CDR tax. And another study that the one cited here has shown that the feedback to land and ocean-based CDR are additive. That is, a combined CDR tax is equal to the sum of the atmospheric CO2 release from the land and the ocean reservoirs they each count. So it has been known, in fact, since 2010, that in response to a reduction in atmospheric CO2, there is an efflux of CO2 from both the terrestrial biosphere and ocean to the atmosphere. And in fact, this CDR feedback was reported in the IPCC reports of 2013 and 2021. But despite this knowledge, most studies on land and ocean CDR ignore the CDR feedback, that is the CDR tax, when they estimate the removal of atmospheric CO2. And doing so without considering the CDR tax provide a gross value of CO2 removal, while including the feedback in the calculations provide a net removal. So this is similar basically to the income derived from a salary. The gross income is the salary before the tax from the atmosphere, that is net CDR. I don't know why it's blocked now. I'm sorry, I don't know what's happening. I'm stuck, I don't know why. Okay, we use as example the ocean alkaline seawater. This is the ocean acidification. So the technique of alkalinization consists in adding to surface waters compounds that will consume hydrogen ions, and this shift this chemical reaction away from CO2 to bicarbonate and carbonate, which causes the absorption of atmospheric CO2 by the ocean. This is CDR, includes a number of chemical compounds. So a recent study estimated the magnitude of the Earth system feedback, the CDR tax, reduces the concentration of atmospheric CO2, which leads to a reduction in land and ocean sinks. And the reduction in land and ocean sinks offsets 56% of the alkalinization-driven capture of atmospheric CO2 by the ocean. So it means that CDR tax is 56%. And therefore, the net capture of atmospheric CO2 driven by alkalinization is only 44% of its gross value, which is less than half the value without the CDR tax. And feedback decreases by about half the effectiveness of all CDR methods in reducing atmospheric CO2 and global warming. So deploying the carbon dioxide removal without taking into account the CDR tax will overestimate the actual amount of atmospheric CO2 by CDR by a factor of about 2. And such CDR will only half of the expected carbon credits, but worse, again, I don't know what happens. That about half the anthropogenic CO2 since 1750 had been captured by natural CO2 sinks, and that the successful CDR will cause a decrease in the concentration of atmospheric CO2, which will slow down the natural and CO2 CDR CO2 sinks. So this can be represented as a mirror image. And the anthropogenic CO2 emission CDR decreases atmospheric CO2, which causes a release by carbon sinks, which increases atmospheric CO2. The two effects are negative feedbacks, which oppose changes. CDR will be limited and constrained by the Earth system feedback, which, as seen previously in previous slides, decreases the effectiveness of all CO2 methods in capturing atmospheric CO2, and also by the competition between CDR and other human activities. And the example of land is the competition for space between afforestation and most other CDR and agriculture for food production. An example in the ocean is the competition in coastal water between seaweed aquaculture for sinking of biomass and for afforestation, reforestation. Because of the above limitation and constraints, land CDR alone could not achieve the goal of removing annually atmospheric CO2 equivalent to more than 30% of emissions. And the only hope of perhaps achieving this goal is to deploy all effective CDR methods on land and also in the oceans, including blue carbon. So I stop here to say, what is the conclusion of all this is that land only cannot achieve the carbon dioxide removal, and we must involve the ocean and the blue carbon as well. So thank you. We'll stop here. So let us escape. So we are now back. I don't know why I haven't lost. Okay. So by our co-chair, so Dr. Zhu from Shanghai Jiao University, who will be presenting a paper on oxygen minimum zone in the ocean. So, Yento, please. Do you hear me?
Yeah, we hear you, but okay.
Hello.
Okay.
Okay. Yeah, this is better. There's something wrong with the microphone. Thank you, Louis. Thank you for the introduction. It's my great pleasure by a lot of collaborators, and some of them are here today. And first of all, so due to the climate change, ocean is, and because of the oxygen is required by most marine animals. So when the oxygen is really, really low, it could cause the death of these animals, such as the crabs shown in the picture, and fishes and oysters. It can also cause coral bleach. So that's why the oxygenation individual species for each kind of marine animals, actually the oxygen, there is an oxygen limit. It's called the P critic, which represents the lowest oxygen pressure that can sustain their basic metabolic demand of that species. And this P critic is actually temperature dependent. That means it varies with the blue line. It shows the species which has very low vulnerability to the temperature. And for some of them actually has very larger their metabolic rate actually also changes, basically accelerates, which leads to more oxygen consumption. That's similar to our human beings. Actually, when we feel stressed, when we feel hot, or when we feel nervous, we will have short breath. So we will breathe more. So that will take more oxygen. And the concentration. And the white line shows the depth in the ocean from the surface to the bottom. And the blue lines represents the marine oxygen. They prefer to live in the environment which has more oxygen than they're required. So in this figure, that will be the region above that marine animal. And here, we also illustrate the definition for oxygen minimum zone, because the right figure shows the dissolved oxygen concentration loss in the surface above 1,200 meters, and bottom shows the depth below 1,200 meters. Obviously, the top layer shows more oxygen loss than the bottom one. And for the oxygen minimum zone, it's basically located in the tropical oceans and the North Pacific Ocean. Together, for the global oxygen minimum zone, since 1960, it has expanded by 10 million cubic kilometers, approximately 2/3 of the Arctic. So that's quite a significant increase. And here it shows the vertical profile of the oxygen minimum zone here. Actually, here is something quite interesting for these several regions. First of all, according to our division, the largest OMZ actually occurred in the equatorial Pacific. And for the smallest one, it actually occurred in the equatorial Atlantic. That's because in the Atlantic, the ventilation is very strong in the Atlantic than in the other oceans. And for the tropical oceans, because the biological productivity is really high, and the circulation is relatively slower in the East Coast. So that's why most of the oxygen minimum zone appears in the east coast of each ocean. And among these oceans, North Pacific is the only. That's because its mechanisms is actually different from the other tropical oceans. That's because in the North Pacific, the water actually has the largest or the oldest water age. So North Pacific Ocean, its OMZ actually is located in the deeper depth compared to the other tropical oceans. And another thing which pay worth attention is is because is for the Arabian Sea and Bay of Bengal. I go back. Okay, this one. Thank you. For the other oceans, we can see there is one maximum OMZ extent in the North Pacific, equatorial Pacific, and the equatorial Atlantic. But in the Bay of Bengal and the Arabian Sea, actually, it has two maximum OMZ extent. It's kind of disturbed. That's because there are two oxygen-rich currents actually disturb the development of the OMZ. In the Arabian Sea, it's the Somali current, And in the Bay of Bengal, it's a Persian water. So because of this intrusion for these two Indian tropical oceans, so it has the two maximum profile. So we compared our estimation to the CMIP6 models. CMIP6 models, they greatly underpredicted the increasing rate of the oxygen minimum zone over the last 60 decades. From here, we can see our estimate is about for the climate models. And then we further checked the habitat constraints due to the oxygen minimum zone expansion. Here it shows the depth. That is one when there is no global warming, when it is purely affected by oxygen loss. So we can see in these tropical oceans and North Pacific oceans, only these regions have the restricted habitat. In other oceans, so there is no restriction at all. And due to the temperature, if the species, they are more sensitive, it increases about 30%. Because most species actually fall in this category. So that means more species are actually affected under the climate change due to the oxygen loss. There are some other cases shown in the top, which means when the temperature increases, they actually has advantage of having larger habitats. But this kind of species is actually smaller than. So here, to test our estimated habitat constraints, we compare our peak rated depth with the real observations. Our observations are actually obtained from the OBIS website. This website provides a lot of historical, and from here, we can see here the y-axis represents the depth difference between our calculated peak rated depth and observed occurrence is different species. So from in their suitable habitats, which means our calculation is actually robust. Our estimates for the adaptation, except the Atlantic cod here. The Atlantic cod, we can see there are about for the Atlantic cod, for this kind of large fish category, actually together with the large mammals, they have a behavior of diving. So sometimes they will dive really fast into the deep ocean. They can hold their breath. They dive just for maybe for food or escaping from their enemies or just for fun. So they have this type of diving behaviors. They can survive in the hypoxia condition for a very short time. So that's why for the Atlantic cod below is increased depth. So since 1960, and the global oxygen minimum zone has expanded significantly, about 2/3 of Arctic Ocean. And the CMIP6 models significantly underpredicted observed OMZ expanding trend. And the last one will be the expanding OMZ or the deoxygenations. And I would like to thank the data providers here, a lot of providers which provides the dissolved oxygen concentration measurements for the animal observations.
A few questions, if there was any from the room or some people online.
And one, actually.
Yeah.
Okay.
Okay, so thank you very much. It was a very nice presentation and exciting annual paper published in 2018, if my memory is correct. Okay, so you show that there is an expansion because of the famous relationship for the rate-win ratio. With extension of the oxygen minimum zone, you also have impact on the distribution of nitrate and phosphate.
That's a very good question. Actually, when I try to explore oxygen minimum zone, I didn't look at the phosphate, but I think these two, I'm not quite sure. I will go back and think more. Yeah, I haven't explored that yet. Yeah. Did that answer your questions? I mean, there's a pause.
Yes, so I think we'll have to move to the next presentation now. So this will be a presentation online by Professor Corinne Lecqueret, who is at the University of East Anglia in Britain. And she is also Corinne.
Thank you. Thank you, Louis, to present online today. I'm going to share my slides here. Okay, can you confirm that you see my full screen?
Yes, we do.
Very good. Okay, so I'm going to talk today about the role of ecosystem. The challenge that we are trying to address is to quantify how much the diversity of marine ecosystems, particularly the lowland jellyfish, but perhaps not the fish at this stage, but limiting to plankton. So how much the diversity in the lower ecosystem, lower trophic level ecosystem influences the carbon cycle in a quantitative way. And the rationaling several elements of the carbon cycle, the morphology, stickiness, and density of organic particles in the ocean, and hence the sinking speed and reminerarization of organic carbon. In this figure, you see a very simple representation of this, where you have on the left-hand side the smaller end of the lower trophic of the zooplankton diversity, and all of these organisms here influence what happens next. So the aggregation of particle, the production of particle, their size, their density. So the plankton diversity really matters structure. So how much the ecosystem is shifted towards to a first level small versus big, but also within this different flavors of small and different flavors of big, will then influence the relative importance of recycling at the ocean surface. So recycling of carbon, recycling of nutrients, the surface sinks at depth, and in particular, at which depth then it becomes remineralized, then turns again into inorganic carbon when it can be recirculated to the surface. So if ecosystems and their activities encourage a cycle that is more axed towards recycling at the ocean surface, change with the atmosphere. If, on the other hand, the ecosystem structure is more axed towards bigger oceans, so the export element of this picture here is encouraged, carbon goes to the deep ocean where it becomes isolated from the atmosphere for decades to potentially millennia. So ecosystems do that. What we want to do is to quantify what is exactly the role of the ecosystem. I should at the end, but it's a process towards a quantification of these fluxes that I want to co-authors in 2009, which we have adapted. So we have adapted the information from that paper here to show that the change in the storage of carbon in the ocean in gigatons of carbon, so this is billion tons of carbon here, is directly proportional to the depth in which ecosystem can play a role. The first one is from packaging, and the denser they are with very big, dense fecal pellet aggregates, the faster they will sink to the deep ocean and the deeper the remineralization depth will be. And likewise, ecosystems can help to, this is again an ecosystem structure. And then there is the chemistry of the particles, particularly calcification, that would move this curve up and down in the graphs that I'm presenting big. So we're talking about easily 100 gigaton of, 100 gigaton of carbon storage changed to the ocean for a remineralization depth change of 50 meters only. 100 gigaton is equivalent to about 50 parts remineralization depth, would translate almost entirely into changes in the air, sea, in the atmosphere. But they would have also, there's also other effects to be expected, of course, just that changes in marine primary production this time would be quite high under a high emission scenarios in 2100, with a reduction of primary production, reduction would have strong implications for animal biomass and fisheries. Convention of color here is flipped for this figure from a paper in Nature Geoscience published by Stephanie Henson and co-author that show that the changes in primary production also directly translate into changes in export production. However, the model estimates for export production varies. Have provided different estimates. There's a factor of 3 between the bottom model and the top model, and in terms of red plus approximately 2%. So modeling these ecosystem changes in the future is really rather challenging. In addition to this, the models have mostly quite simple representation of ecosystems. The models used by the IPCC had on average between 1 to 3 phytoplankton and maximum 3 zooplankton. Most of them have by nutrient availability and not so much by the ecosystem dynamics. So we have, in my research group for a number of years now, developed an approach to grouping marine organisms into plankton functional types. And a plankton functional type would be included with an organism's, for example, diatoms, role, a set of distinct traits so that they can be modeled uniquely from other PFTs. They should have distinct effects on others and be of quantitative marine ocean workshop that were held at the Laboratoire d'Oceanography of Villefranche-sur-Mer, where Louis Legendre has worked for many years and was director of the institute. We defined phycophytoplankton, diatoms, Phaeocystis, and a mixed phytoplankton, bacteria, and then 5 types of zooplankton, jellyfish. Now, once this ecosystem is defined, then it interacts, so plankton interact with each other, mostly grazers eating the grazers that are smaller than them. And then presenting this organic carbon export here, which involves decisions on particles. So they have the choice So the resulting fluxes from the ecosystem can go into either dissolved carbon, that's mostly what comes out of phytoplankton autotrophic respiration, or go into a small or a large particle. The large particle sinks at different speed depending on its density, which is mostly measured as a function of ballasting from either silica shells from diatoms or diatoms being grazed by bigger organisms, or calcium carbonate shells from copoetophores or pteropod. And so this modulates the model. So this is a huge advantage compared to models that are more aggregated. And I show you the example of diatoms here. They are about of temperature. They are shown with small dots there. Then decisions come into how these are going to be represented. And so here I'm going to go show results from 3 branches of this model. One of them has used 3-parameter growth with an optimal temperature condition fitted through optimal growth for all the PFTs that is fitted at the top 90% of the data, with the logic that this is the type of plankton that will grow the best in that temperature range. We do this as feed on smaller preys, and we limit the difference between the plankton functional type as much as we can to the documented rates. We've built the PFTs one at a time, so each of them has a little scientific insight behind. On the examination of the rate, you see that if these are all the PFTs, phytoplankton on the left-hand side and heterotroph, the growth rate increases from the smaller to the bigger phytoplankton and decreases from the smaller to the bigger heterotrophs. So this is a result in itself. Now, what happens when you put these equations in the effects of ocean currents, temperature, salinity, and the dynamics of the ecosystems is that if you have this plankton functional type, reproduces the observations much, much better than a model that is more like the ones that are used for Earth system models today, which have very sluggish gradients in chlorophyll, whereas the higher the PFTs, the more trophic levels you have, the sharper the gradients, and also the more reaction of chlorophyll in the north compared to the south as observed. So what we have done next is at the bottom, we have our historical branch, which is to the left-hand side, then a branch in the middle that is kilometers in this model, and the right-hand side, which has optimized the carbon fluxes. These models behave very differently, and this is what becomes interesting. So on the left-hand side, you have the phytoplankton, those are there. You see that for our historical model, the model outcome, the emergent properties, the big and the small, whereas for the echo, which is our best model, probably closer to reality, I'm going to wrap up in 10 seconds, is about halfway between the two. When you trickle this down to the carbon fluxes, what you see, I won't go in detail here, but what you see is that you have a very different distribution and outcome for carbon fluxes, 50% in the quantification of export, primary production and export production in the process of validating with observations. So that has by itself some challenges, but understanding where the reality lies really depends on us being able to get a grip on what are the lower trophic ecosystems today. Thank you very much.
Well, thank you very much, and many more years to come, I guess. We could discuss all these presentations, all the move to the next talk by Professor Zhang. And then she is at the South China Sea Institute of us about radiolarians.
Okay, thank you, Luis. Good afternoon, good evening, everyone. My name is Zhang from the South Chinese Institute of Oceanography, Chinese Academy of Science. I'm very honored to attend this great forum and to present our study. Today, my topic is about first, let me introduce the research background. This powder-like matters is from and the background. You can see a large amount of specimens. They are white and clear. They but delicate structures. So yes, they are all radiolarian fossils with siliceous skeleton makes them become good process of oceanographic and if you compare the morphological structure of flesh radiolaria in the water and those fossils from the sediments, you can know they are very well preserved in the sediments with a very slight dissolution. So this makes them become good proxy to oceanographic reconstruction. As a single-celled microzooplankton, radiolarians are crucial to abyssal sea. Many species bear algal symbionts, so they are unique source of opaline silica over the water and play important roles in the biogeochemical cycles of silica and carbon cycles. But currently, very little is known about them. Very difficult to keep alive in culture. Furthermore, this all the study global research size dead and living specimens. Only a few studies touched more than 1,000 water depths. So regarding the species diversity in deep sea, compared to the study is very insufficient. So that's why our research for the present is the key to the past. So let's move to our process of modern observation. We merely use the mixed multi-net plankton distinguish dead and living specimens. So, so far about radiolaria taxonomy, there are so make all the species plants occurring in the tropical Indian Ocean and the Pacific Ocean. And during this process, we often encounter many species have bear the depi. Oh, sorry. Plankton samples in the northwestern Pacific and analyze their fluorescence patterns. We identified 37 species have obligate hollow beams, indicating their living depths controlled by light availability. But some species, for example, Ocasodesmia, lack photosynthetic column beam, has understanding of why radiolarians in oligotrophic open sea are not so significant role in the future silica carbon cycle in the open Ocean. In the northwestern Pacific axis, longitudinal difference influenced by warm or cold water species can be used to study historical evolution of water mass. Analyze the 76 surface water surface present that across the Beijing scale, the local same region regional environments, the radiolaria abundance or community structure and species abundance all experience significant monsoon. Radiolaria vertical distribution in the Indian Ocean. The samples 1,000 depths. We know radiolaria assemblage at different depths. So we recognize this species only living in surface water, which can indicate the surface water condition. Living in the in subsurface water, they can reflect the subsurface. According to the vertical distributions of living species, we can identify the radiolaria forces record to reconstruct the dynamic change in the vertical structure of water. So this another science data results. You can see there's there are the depth species composition have their living water condition. So radiolaria indicate we can application of the paleoceanographic reconstruction. One application is about Pacific. So another application is about dynamic evolution of water structures. This card is from the Okinawa Trough. We on the basis of the vertical distribution of living radiolarias, we identify the radiolaria forces record. In contrast, an increased APIW occurred during the last declaration, especially during two cold events, and with a weak intensity over the horizon. Notably, there was a rapid decline in APIW intensity at the neo-glaciation, similar to the KC, which was related to the high latitude and low latitude linkage. Deglacier and Holocene variability in North Pacific upper and the Indian intermediate. In the future, we will continue to focus on the on biological process and the ecological adaptation to various environmental change. Because a recent study indicates that the global change would trigger diatom biomass decline. And radiolarias, another dominant plankton siliciferous, may be more important roles of marine silica cycle in the future. And further, we will also strengthen interdisciplinary. Micro zooplankton is very tiny and light. It's If you want.
Okay, let me introduce the last speaker of our session, Dr. Laura Airodi, who is a fellow of European Science Academy of Sciences, and will talk about challenges on the active restoration of coastal ecosystem. Let's welcome Laura.
Thank you. Can you see the screen?
Yes.
Okay.
We can see the screen, but it's not
Okay.
in the. Oh, now. Okay, perfect.
Is it okay?
Yeah. Yeah.
Okay. Thank you very much. So my talk is about the challenges of the active restoration of coastal ecosystem. I start introducing why we need full large-scale restoration efforts that address concrete societal issues, and this can help move restoration and conservation. Examples of success stories from Venice Lagoon, that is where I work at the moment, and about the outcomes of the large-scale sword mass restoration that have design challenges. Over the century, we have lost a large portion of marine habitats, and recent estimates suggest that we have had losses that go from 30% to 85% for most of our coastal ecosystem, with a consequence loss of ecosystem services that has been estimated to range around curbing this degradation of marine ecosystem in parallel and partially driving the loss of natural ecosystem. We have assisted to a largely overlooked global sprawl of built-up areas that nowadays occupy like 32,000 square kilometers of our sea bottom, impacting from 1 to more than 3. And this sprawl is growing massively by 57% over about a decade. And this is for all sorts of activities. On land, we have had this process of strong modification of our landscape since a long time, and we have been more aware about the issues, and we have been also more active in investing in green spaces, green buildings, and other active approaches to restore in some way also the green infrastructure in this highly modified ecosystem. When in the ocean, there have been more kind of passive conservation, decade on nature restoration, or the ocean science for sustainable development, or in Europe, the recent people seems as something that is restoring something that was lost into the past. But nowadays, restoration is it's not possible to restore what was there in the past because we are in a highly novel ecosystem. And nowadays, active restoration includes multiple interventions that both aim to accelerate or enable recovery, but also could serve, for example, to redefine functional and healthy nature-based solutions. Nature solution is a term that was first introduced by the World Bank in 2008. Different definitions about this, and a recent review have identified that there is a core on common points in all these different definitions, that they should all be inspired by nature, face societal challenges, provide multiple benefits, including some kind of biodiversity gain, and be efficient and effective. I'll talk about nature-based solutions because they are a tool that can fuel large-scale marine restoration by addressing concrete societal measures to climate change, and to combine effective, for example, cost adaptation with talks. I've also questioned some of these effectiveness, for example, in terms of mitigation. I'll focus more on adaptation. That's the area. So adaptation is an increasing need of coastal areas that face increasing threats from erosion and flood risk with damage to people, infrastructure, and tourism. These are data from the team by Robert Nice at risk from severe flood risk will more than double in the next few years, reaching all. So far, hard engineering has been the most common approach to coastal protection. This is a view of the North Adriatic coastline, and it's and poor ecological performance. For example, we know well that they are corridors for invasive species. Further, they are widespread aging and they are outdated at different sea level. And the World Bank has estimated the cost of more than 18 trillion US dollar to adapt and maintain all this green infrastructure. And this has led to the need to think more about alternatives, like ecosystem-based alternatives, biologically active in some way, to the most softer approach where you only rely on the restoration of ecosystem. Like, for example, this is an oyster reef and a salt marsh that are restored as a system for coastal defense. The majority of the intervention probably follow into what we call hybrid project. That's when you integrate restoration as part of a hard coastal adaptation, but you reduce the amount of hard structure that you need because part of the defense is taken up by the restored ecosystem. To work and to study, and where there has been serious attempt to solve some of the societal needs in the arsenal. For those who know, Venice Lagoon is the largest lagoon system in Italy, full of natural and
concentration of particle through depth. You really see this profile where at the as a function of depth. So thank you for your question.
Well, we could add that there is an interesting connection between this aspect and the zones of minimum oxygen, because of course,
then the change in ecosystem to know.
Okay, I have a short version, a longer version. You know that I guess everybody knows about the short version. We used to think that when warms the ocean, we stratifies the ocean, less input from below in the surface waters, so less nutrients. Especially this, you decrease particularly the condition, favorable condition for the diatoms. We see and inside, okay. Where, of course, Southern Ocean is very specific for phytoplankton, and so this is not true for the for the atoms in the Southern Ocean. But you know, the question is more larger than that, because you are using radiolarian, rhizarian, or whatever the name. Okay, what is the effect of climate change on this kind of organism? Application processes that is responsible for the deposit of biologic silica in this organism. And they might be very different compared to the atoms. And so you have to go a bit deeper into the story to understand all the process by mail so that we can maybe identify possible progresses for the future. Thank you.
Okay, thank you. And recently,
yes, but it's very
funding, and whether you allocate to one area, then there are less funding for the area. But the truth is that they should go hand in hand. You must do both mitigation and adaptation. And nature-based solution can have different roles for both. I mean, for mitigation, they might be less relevant than in adaptation, for example, something like that. And indeed, I actually wanted to ask you a question, because I mean, carbon dioxide removal, ocean-based or land-based carbon dioxide removal can be not so effective because of this carbon taxation, how you called it. But I was wondering, is that consider like for example, carbon sinks like in the salt marshes or seagrasses on the deep sea that tend to be more stable. Is it responding so quickly they work as sinks?
Yes, well, none of these feedbacks are immediate because anyway, you know, to a year or two, it will take the ecosystem. And the negative feedbacks will also be at that kind of scale. So we have to think in the proper scale, but it is probably not, you know, the scale. It's probably a decadal scale, both for the carbon dioxide removal to prove their effectiveness, to become effective, and for the responses to occur. And I agree with you that depending on the types of systems, well, the response may be slower, or and that when we intervene on the atmosphere, while there is well, a response of the natural things. And in fact, what is interesting is that is this mirror image, that is, it already happened. And we are quite happy that it happened, that half of the by natural reservoirs. So we don't have to be surprised that when we try to do the opposite, that is to remove CO2 from the atmosphere, up to now, we have just been putting CO2 into the atmosphere. When we do the reverse, well, nature responds in a sense, logically, exactly the same way. Half the CO2 we have managed to bring down is compensated by a release of about half. So it's since 1750 was about organic CO2. Now that we want to remove, because if we don't take into account, it means that when we think, okay, oh, we have managed to remove, let's say, 100 units, the net removal is just 50. So we have to be careful about that if we want to avoid any continuous increase in CO2 after we have, well, let's say, after 2050. When
if I can, Hervé Clostre speaking. My question is for Corinne. Model with 6 PFT and a model with 10 PFT, and the improvement, especially in the model of 10 with respect to the model of 6, the additional PFT sequentially or all the 4 together, and how can you explain?
Thank you, Hervé, in that we developed the 10 PFT model and then we killed 4. And we killed them all together. Parameter, I won't go in the detail. But the most important changes that we have made for this dynamics is the vision of a slow-growing macrozooplankton krill. And because it is growing zooplankton, the copepod in particular, and that introduced of the chlorophyll or the phytoplankton biomass in the Southern Ocean summer in a way that the Northern Ocean. So it was really the introduction of trophic dynamics that helped to put this chlorophyll down in the ocean. Since we published this study, we have since added 2 more, I think 4 trophic structure with the system that we have. And we have much more sharper gradient compared to when you have just the essentially 2 zooplankton that is more conventional.
Thank you.
I mean, this also, perhaps I can bring the first speaker into this discussion because I think that the grazing from fisheries would also be eventually important, mortality term. But if you then have variable fisheries on top, you would also, Professor Tong.
Yeah, actually, I want to answer try to answer the question. My name is Zhang from Yellow Sea Fisheries Research Institute. Actually, the agriculture, especially for the shellfish and seaweed farming, is a kind of biological pump. They absorb the CO2 almost the same way with the should be the concept of the carbon sink fisheries should be focused on the ecosystem based, and phytoplankton focused on the time scale of the carbon, such as there's some opinion for the scientists. They are debate for the shellfish is the carbon sink or carbon source. But Dr. Ed Academic Tong, the presentation showed that clearly data showed that almost only reaching and calcification. So that's an ongoing work now as we try to trace the seaweed or the phytoplankton. So if the CO2 is higher, CO2 in the atmosphere in the seawater should be much higher than atmosphere. But the evidence from the large scale agriculture, we cannot detect this phenomenon. That means this issue, the CO2, where it goes, should be this ongoing work. But anyway, from my opinion, the agriculture, especially the looking of the climate change. Thank you.
Okay, lifetime of each carbon sink way is comparable, or there is big difference, such as macroalgae sequences carbon and biological pump. And
Ready. Professor Liu,
okay.
keynote.
Okay. Now I actually have a
Yeah, actually, if we focus on the shell, will be keep in a very long term, more than 100 years. But if just we focus on the soft tissue, here. But just the family, the deep. This different with that means information. But also the CO2 from between plankton, we can equals.
Some showed it the reference now. If you want.
Future, because in the visualization now except our